Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. And if you need global distributions, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. And for your machine learning workloads, they just announced dedicated CPU instances. Go to dataengineeringpodcast.com/linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. This week's episode is also sponsored by Data Coral, an AWS native, serverless data infrastructure that installs in your VPC. Data Coral helps data engineers build and manage the flow of data pipelines without having to manage any infrastructure, meaning you can spend your time invested in data transformations and business needs rather than pipeline maintenance. Raghu Murthy, founder and CEO of Data Coral, built data infrastructures at Yahoo and Facebook, scaling from terabytes to petabytes of analytic data. He started Data Coral with the goal to make SQL the universal data programming language. Visit dataengineeringpodcast.com/datacoral today to find out more. And having all of your logs and event data in one place makes your life easier when something breaks, unless that something is your Elasticsearch cluster because it's storing too much data. Chaos Search frees you from having to worry about data retention, unexpected failures, and expanding operating costs. They give you a fully managed service to search and analyze all of your logs in S3 entirely under your control, all for half the cost of running your own Elasticsearch cluster or using a hosted platform. Try it out for yourself at dataengineeringpodcast.com/chaos search, and don't forget to thank them for supporting the show. You listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Corinium Global Intelligence, Alluxio, and Data Council. Upcoming events include the Data Orchestration Summit and Data Council in New York City. Go to dataengineeringpodcast.com/conferences to learn more about these and other events, and take advantage of our partner discounts to save money when you register today. Your host is Tobias Macy, and today I'm interviewing Sean Knapp about Ascend, which he is billing as an autonomous Dataflow service. So, Sean, can you start by introducing yourself?
Yeah, hi. Thanks for having me, Tobias. I'm Sean Knapp, the founder and CEO of Ascend.io.
And do you remember how you first got involved in the area of data management?
I do. It was actually at the very start of my career. This is back in 2004. I just graduated college as a computer science major and ended up starting at Google on the front end engineering team. And part of our big mandate was to do a lot of experimentation with the various sort of usability factors on web search, really trying to get better engagement with our users. And a lot of my academic background was around cognitive science and human computer interaction. And what I found very quickly was in experimenting with all these usability factors in our users, I actually ended up spending far more time writing data pipelines to analyze the usage of our users. As you know, when you're at Google scale, simply trying to figure out what your users did yesterday required pretty remarkably sized infrastructure and sophistication to inform what you should do next and the efficacy of what you had done before. And so very quickly, I went from being a front end engineer to specializing deeply in data engineering and data science.
And how did you find that difference in terms of the tool sets going from a front end engineer to dealing with a lot of back end data processing?
It was incredibly different in that front end is a very visual experience. You have what I think are fairly mature tools and technologies. When we went into a lot of the data processing domain, what I found was the raw capabilities, the ability to store and process data at incredibly large volumes, was quite mature. The rest of the tooling and ecosystem around that wasn't as advanced. And that was sort of my first experience in data management and pipelines in general was it's very easy to write a pipeline to do a thing, but to write many pipelines that depend on each other and interconnect and do more sophisticated and advanced things together really became a lot of that challenge that I observed really early on in my career.
Yeah, it's definitely interesting how a lot of these tools have developed from, as you said, being very technically capable, but they leave a lot of sharp edges that you can happen to harm yourself on if you don't know exactly what you're doing and have a lot of background in the space. And it's interesting to see how the industry has been progressing to add a bit more polish and safety features into these systems to make them easier to approach.
Yep, I wholeheartedly agree. And I think it's something that we see in the natural evolution of many technology domains. And I think that this is really sort of the big encumbrance we find today, and the thing that makes life as a data engineer more challenging, to put it simply, is just trying to maintain these powerful yet brittle and finicky technologies is really becoming one of the larger pain points of modern day data engineering.
So, can you start a bit by explaining what the Ascend platform is that you've been building?
Yeah, I'd be really happy to. So, about 4 years ago, uh, we sat down and took a look at the data ecosystem and said, look, like we've been building complex analytics and machine learning and data systems for really the last, at that point, it was the last 11, 12 years of my career. And one of the things that really wanted to try and tackle was how do we make our lives as data engineers easier, more effective, and simpler? We feel like we're constantly reinventing the wheel, constantly being paged at 3 in the morning. There must be something better. And so the sort of core thesis behind Ascend was, what if we could create a new technology, something that's not a storage or a processing system, but instead a control system, similar to what we've seen in other industries and other domains. For example, like how infrastructure now has Kubernetes, a declarative model for infrastructure that has an intelligent control plane that orchestrates the underlying infrastructure. Could we do something like that for data pipelines? And so we spent a good bit of time really architecting what would a declarative model look like for data pipelines, and can we architect an orchestration system that provides this control plane that pairs both declarative configurations and code with an intelligent control plane to automate a lot of the operation, performance tuning, and scaling of data pipelines that to date we had had to simply manually code.
And can you talk a bit more about some of the background and origin story and your inspiration for creating it in the first place and some of the aspects of the problem space that you're working in that keeps you motivated?
Absolutely. So one of the things that was really motivating is, a few years before I started Ascend, I spent a lot of time with our engineering teams building these pipelines that, simply put, we felt that we could describe these, what were fairly big, hefty pipelines with a handful of SQL statements. Yet we found we were writing a ton of code and dealing with incredible pains of maintaining those systems due to the intricacies of the data and challenges like late arriving data and deduplicating data and failures in the underlying systems. And so we took a step back and said, well, there's an innumerable set of heuristics and problems that we encounter here. And when we think about it from an academic perspective, we have great pipeline, or we have a great processing technology, and we have great storage technology, but we don't have a pipeline engine. When I use a database or a data warehouse, there's a query planner and a query optimizer that run and optimize with that database engine. We don't get the same thing with pipelines today. We're, in essence, re-implementing database query planner logic every single stage of every single pipeline. And this seems like a really interesting and incredibly hard challenge to solve. But if we can solve that, we can truly introduce a new wave of data engineering and get ourselves out of this data plumbing business and far more into data architecting business. And so that was really excited to think through what we could actually enable across the ecosystem if we got people out of the muck.
And my understanding is that the foundational layer for the platform that you've built is using Spark. So I'm wondering if you can talk a bit about your criteria for selecting the execution substrate for the platform and some of the features of Spark that lent itself well to the project that you were trying to build.
Yeah, that's a great question. And so, interestingly enough, when we originally started Ascend, we started with BigQuery as the execution engine. As we started with a simple SQL dialect because it was entirely declarative in nature, and we knew that BigQuery was a very scalable engine. And obviously, as a result, we operated purely in the Google Cloud environment. And the idea behind this was in those early stages to really just prove out the concept of this declarative pipeline engine and orchestration layer. And as we proved that out and found that we could really solve some pretty powerful and compelling challenges, we then started to change our focus to how do we make this extensible to multiple compute engines? How do we make this extensible to multiple cloud environments? And that's where we started to do a lot of our research. We looked into Beam, we looked into Spark, we looked into a handful of other technologies, and also interviewed a lot of our friends and customers and so on across spaces or in industries. And we found that Spark was the just simply most popular. It was one that we had the most expertise and understanding in house, and it was one where we felt we could really provide a multi cloud, multi platform advantage. And for developers, one of the things we also found was there was a strong desire to want to still build for Spark, just simply not have to deal with the brittleness and the finickiness of it per se. And so we actually found some really cool capabilities of doing the approach of not only can we manage a Spark infrastructure for you, but we can remove a lot of the scaffolding around using Spark and really focus a lot more of the engineering time on data frame transformations and logic, as opposed to parameterization and tuning and tweaking. So we found we could get not just this multi cloud and multi platform benefit, but really could expose Spark to our users in a way that was really compelling.
And I'm curious, what are some of the sharp edges and limitations of Spark that you've run into in the process of building on top of it? And if you were to rewrite Spark from scratch today to fit your particular set of requirements, if there are any aspects of it that you would change?
Yeah, I'd say we've there's a bunch of tweaks and nuances we've done over the course of, for example, as we became HIPAA compliant, like we had to do quirky things with how do you manage both encryption and compression of data as it's being stored and in transit, and things that just weren't quite properly supported there. But I'd say like these are always just like the small sharp edges you find. The really big interesting one that I would love to see Spark even more fully embrace, and they're doing a lot more with this in 3.0, is native Kubernetes support. We're really big fans of running Spark on K8s. We actually have been running K8s as an underlying infrastructure since January of 2016, and all of our Spark usage today all runs on elastic Kubernetes infrastructure. And so, really continuing to invest in that tight connection between Spark and Kubernetes for us has been an area of extreme interest.
So, can you describe a bit more of the technical implementation of Ascend?
Yeah, the our technology itself really works at a couple of different layers. At the infrastructure layer, we've designed to run on all three clouds, that being Amazon, Azure, and Google. And as a unified infrastructure layer, we run two Kubernetes clusters. One is for what we call our control plane. That is all of our microservices that operate at the metadata layer. It's about 15, maybe 20 microservices now, a combination of Node, Golang, and Scala services that mostly talk gRPC to each other and build a pretty cohesive model of what's going on in the system. And I can dive more into that. And then the data plane is the other Kubernetes infrastructure. That's a elastically scaled on spot and preemptible instances that runs both kubespark for a lot of our Spark infrastructure and also runs workers. These essentially autoscaled Go-based workers that we use for a lot of processing that sits outside of Spark, where the shape and model of the work required fits better into a custom set of work that's run directly on Kubernetes as opposed to in Spark. But both of those run inside of this elastic compute infrastructure.
And what are some of the ways that the implementation details and the overall system architecture have evolved since you first began working on it, and some of the assumptions that you had going into the project that have been challenged or updated as you started to get deeper into the problem?
Yeah, I'd say one of the key things as part of this notion of declarative pipelines is the core engine that operates on everything is this control plane. Control plane's responsibility is to take this blueprint that is the output of the data architecture and continually compare it against the data plane, uh, essentially what has already been calculated and what exists today. And that control plane has to answer the questions of uh, does what I have already existing in the data plane reflect the blueprint at the logic plane? If it doesn't, what needs to be regenerated or updated or deleted, and how do I dynamically do this? And so when we first architected the system in that control plane, the idea behind this was, well, let's inspect the entire graph. And so you apply a bunch of compiler theory and you do a bunch of things like we SHA not just the data, but all the transforms that we're performing recursively all the way down to the data SHAs to try and rapidly determine have we done the appropriate work or do we need to do new work? But what we found is even at scale, uh, this becomes hard. And so we started to invest a lot of time and energy in answering the question of what happens if I'm tracking not just 10 or even 100,000 transforms that may have millions of partitions of data, but what if I'm tracking hundreds of millions or billions of partitions of data, not just records, but actual individual files? How can I, within a second or two, rapidly determine whether or not my blueprint actually matches what exists in the underlying storage layer? And so this was one of these huge areas of investment where we spent well over a year for a big chunk of the team building the next generation of our control plane to be able to do that, essentially inspect this massive underlying blueprint of data, or the massive blueprint of data and the underlying physical state of data, and within a matter of a second or two, tell you what new work has to be done. And that was probably one of the biggest undertakings that we've had to go through as a company.
And in terms of the interface that an end user of the Ascend platform would be interacting with, how does that compare to the Spark API? And what are some of the additional features and functionality that you've layered on or changes in terms of the programming model that's available?
Yeah, the interfaces themselves, from a sort of a tactical perspective, are similar in the sense of there's command lines, there's SDKs, there's APIs. We also offer a really rich UI experience too, as you can navigate the entire lineage and dependency of all the various data sets and where they came from and get the profile of data on them and so on. I'd say the mental model, however, is slightly different. When we think of how our data flows work, they are separated from the execution layer in the sense of there's no job that is run, right? So when you send something to Spark, you're saying run this job. When you send something to Ascend, you're saying make it so. And so the fundamental sort of approach is you can send declarative instructions to Spark, but it's contained within a task or really a job itself, not a task in Spark's vernacular. And so the idea behind this is what if you could take not just one job, but your entire world of jobs and make those all declarative? And so I would say that if Spark were to have a perpetual query planner and optimizer that looked across all jobs that it had ever done before and understood the storage layer as well as the compute layer and the dependencies between those, That's kind of how Ascend looks at it. And so, even we've spent very little time trying to optimize how Spark itself runs, but we've spent a lot of time trying to optimize what gets sent to Spark. And so those paradigms are I think best summarized as the difference between imperative programming models and declarative programming models.
And my understanding is that in terms of how somebody would actually create a desired end state with the Ascend platform is by writing these series of transforms, which you guarantee to be side effect free. And so I'm wondering if you can talk a bit more about that mechanism and some of the ways that you ensure that there are no side effects that in the transforms, and some of the challenges in terms of the conceptual model that engineers go through coming from Spark and working with Ascend.
Mm-hmm. Yeah, I'd be happy to. So, trying to have transforms be side effect free sort of fits into a couple of categories here. One thing that we did, and was one of the benefits in starting with SQL, is we can parse that SQL and we can analyze and understand that SQL, the output schema, the inferred partitioning mechanisms, and really optimize that in harmony with the downstream transforms in SQL that is working with, or that is working on that data. And so part of the ability of avoiding the side effects is if you start first with a language like SQL, it makes it much easier for us to always know where a piece of data came from, why it got there, and whether or not the calculation is in that partition is still valid, or did something upstream change and it needs to be recalculated. And that was because we could just parse SQL really effectively and understand what that dependency chain is. So that was really where it started. As we opened up more uh, PySpark and data frame transformation capabilities, it really became a balance of exposing a lot more of the raw horsepower and capabilities while asking users to inform the control plane enough with hints so that things like, is this a full reduction? Is it a partial reduction? Is it a straight map operation? We can infer a fair bit from those code snippets, but we at the same time do need the developer and sort of architectural assistance to properly optimize that system. Then what we did is at the underlying layers, we've put in a lot of work into our storage layer to do things like a lot of optimization around deduplication. So, for example, before we ever send any task to Spark or any job to Spark, we first look and say, well, what's the transformation that is being done, and on what sets of data is it being done on? And have we ever done this for any data pipeline anywhere else in our ecosystem? And is it possible to optimize it? Is it already actually sitting in S3 or GCS or Azure Blob somewhere? And if it is, we don't even have to send that work. We can simply leverage the same piece of data. And so that optimization layer tied with much more of a functional execution model where we never overwrite that individual piece of data, but instead introduced a safety layer of atomic commits at the metadata layer, allowed us to ensure that no data was ever propagated unless it passed the integrity checks and was properly committed and became a new update of that model. And so it was this combination, to recap, it was this combination of much more declarative models, understanding of the developer's intent, that then informs that control plane with the safeguards of functional programming models tied to safety checks like atomic commits and integrity checks to guarantee that nothing ever flows through that shouldn't actually be there.
And my understanding too is that in addition to the execution layer, Ascend has the concept of a structured data lake capability as well. And I'm wondering if you can do a bit of compare and contrast between what you're building there and some of the capabilities that are available through Delta Lake.
Yeah, I'd be happy to. So, what we did with Ascend Structured Data Lake is we said all data that can be managed and exposed via the structured data lake is really outputs of various pipelines and data flows. And what we can do as part of this is leverage all of the underlying metadata that we collect where we know how to do things like dynamically partition the data based off of the transforms that are being performed and what we understand already about profiling of the data. We can also do things like guarantee atomic commits and atomic reads of the data, again, based off of really inserting this abstraction layer between where you're accessing the block level, if you will, of data, or the partition level within a blob store, and the metadata layer to ensure that level of consistency. And so for us, our approach around this was really oriented towards, can we ensure that you have a well-formed, well-structured data lake that is directly reflective of the pipelines that operate on it and exposes more of that metadata. But I'd say about Delta Lake, which is a really cool technology too, solves a slightly different problem, which is, you know, at the core is, how do you insert additional data that gets your data lake to behave a little bit closer to how a data warehouse would be, where you can get snapshotting and compression of data as you're incrementally adding to those data sets. It has a handful of other really cool capabilities as well, but I would say that they both would work in concert with one another, but solve different problems.
And for a data engineer who is onboarding onto the Ascend platform and looking to complete a particular project, do you have any concrete examples of what the overall workflow looks like and how that fits into some of the broader ecosystem of data platforms?
Yeah, we do. One of the things that we've opened up that's pretty cool for a data engineer that wants to try Ascend is literally, we have examples of this now on a weekly basis where uh, folks literally go to our website. You can get straight access to the product in a trial environment without ever having to put in a credit card or talk to anybody. It's literally instantaneous to start building on the product. And then really that experience and how they integrate into their existing systems. We've worked pretty hard to make this seamless, and it's actually one of our metrics and our goals of what we're trying to optimize is, as you drop into any sort of a trial environment, or if you were already a customer and you have that, is you simply create one of three core constructs. It's either a read connector, a transform, or a write connector. And so most users obviously start first with a read connector. You describe where your data is sitting. It could be sitting inside of S3 or Redshift or a Kafka queue. And as you describe that, you literally point Ascend towards it. And Ascend will start actually listing it out, analyzing the data. If it's not snappy compressed Parquet files, we're going to convert it and store it internally for you, so it's optimized for Spark automatically. And then you can actually just start building against it. You can do things like we have a capability called queryable dataflows, where any stage of any data pipeline we expose like a warehouse, where you can do just dynamic ad hoc queries and then rapidly convert those to full stages of pipelines called transforms, and vice versa. And so the iteration process becomes really quickly to start to build up a few stages. And then either on the tail end, the way that it works is we make it really easy to either write your data back out, Redshift, BigQuery, S3, GCS, ABS, etc., or actually access the data if you're trying to put it into like Tableau or Power BI or others. We have SDKs and APIs, as well as a URL structure for embedding those straight into other systems to read out the records or the raw byte streams from any data flow. So we've added a lot of these capabilities to try and make it as fast as possible to be able to create that end-to-end hello world experience, if you will.
And can you also talk a bit more about some of the pipeline orchestration system that you've built into Ascend and some of the overall benefits that that provides to data engineers as well?
Yeah, I'd be happy to. At the pipeline orchestration level, the really key benefit of this goes back to what we talked about, which is that shift from an imperative system to a declarative system. The benefit of this is that we get to automate and offload a lot of the painful pieces of things like, well, what happens when you have late arriving data? Do you need to shift how you're partitioning of that data, or do you have to retract previous calculations and update them and propagate them through as a result? So things like that end up being handled in a declarative model, as the system itself simply analyzes and detects what data has started to move through, what data already moves through, and knows the lineage and dependency of those. And so what we found is it's much faster to architect and design these pipelines and get them deployed out in scale. The other big benefit that we've seen is the deduplication factor that we get with a lot of the underlying infrastructure and storage, and as well as the pipelines, allows us to do things like rapid branching of pipelines that don't require reprocessing. And so as we are able to take an existing pipeline that may be running in production, you can simply branch that like you would branch code and only modify bits and pieces of that. And the only reprocessing that's done, even if you're developing on it, is really just the deltas, the changes to that data set and that pipeline versus having to reprocess everything. Then I'd say that the third piece that's also related is we remove a lot of the scheduling burden. You used to have to set, like, I want to monitor these data sets at these times with these timers and triggers and check for these parameters. And even as you're gluing together different DAGs of pipelines, there was a huge scheduling burden to actually pair all of these together. What we figured out was we can actually remove a lot of that and simply make it far more, hence the name, Dataflow-esque, based off of the data models as opposed to a scheduling and trigger-based model.
For people who have existing investment in the overall Spark ecosystem and existing Spark jobs, is there a simple migration capability that you have available as far as being able to translate their existing jobs to the new programming model or run them directly on Ascend while they work on remapping them to the paradigms that you are supporting? Or is it something that they would have to do it piecemeal where they just do direct migrations from the existing infrastructure and then do the translation to deploy onto Ascend?
Yeah, that's a really good question. We've definitely worked with a bunch of customers to really accelerate that migration path. One of the really cool things that we found is that ability to both simplify the code as it migrates over, and then also optimize a lot of the pipelines themselves. One of the best examples is actually a case study on our website. We were able to, as part of the migration process, cut out 98% of the code required for a particular use case, simply because so much of this was the scaffolding around spinning up Spark and managing the parameterization and tuning versus the actual architecture of the data and the system itself. And so what we find with a lot of our customers as they start to build on Ascend is that ability to either integrate into their existing pipelines or rapidly migrate that over in a much simpler declarative model to Ascend itself. The other piece that I think is super important to highlight is we are really big believers that your tech stack isn't going to have just any one piece of technology, right? Like, you're going to run some stuff with Ascend. You're going to run some of your own Spark stuff probably, or Presto, or some other Hive or Hadoop cluster. And as a result, this is one of the reasons why we launched the notion of this structured data lake is, hey, let's actually give you the ability to put your own Spark jobs, your own Hadoop jobs, or even put up notebooks directly accessing the underlying optimized internal storage layer of Ascend, so that we can really plug in just like any other piece of your infrastructure. It's just an S3 compatible interface at the end of the day that can hook into any of the rest of your tech stack.
And my understanding is that for providing that S3 interface, you're actually using the MinIO product for the gateway interfaces on top of the non-S3 storage system. So I'm wondering if you can talk a bit more about that and some of the other technical specifics of the structured data lake as far as the file formats or schema enforcement that you have in place.
Yeah, so the MinIO gateways was super cool. Like, we're really big fans of the technology. What we essentially did was uh, every environment that we stand up has that gateway running. And the sort of classic MinIO approach is to map an S3 compatible interface to Azure Blob Store, Google Cloud Storage, or a Hadoop file system, or a plethora of others, but really sort of preserve the same file path structure, more or less. And what we did that was really fun was we grabbed that and created a different handler inside of MinIO that rather than mapping directly back to any particular blob store, first talk to our control plane. And the idea behind this is because we do all of this advanced deduplication of data and jobs and tasks, not too dissimilar from how you would see like a network file system does block level deduplication. You have to actually construct a virtual file system based off of the metadata itself. And so as you're listing out the data services and the data flows and all the underlying data sets that you have access to, that MinIO gateway is actually talking to our control plane and saying, hey, what is the actual file path structure and system in place? And even listing for the underlying partitions of a particular data set itself, maybe digging into all sorts of different directories and structures that are just optimized, that are shared across a lot of the sort of upper component level model, but just optimized and deduped. And so that communication model required a bunch of optimizations that really tuned for performance and so on, but gives you, in essence, a really consistent and elegant S3 compatible data lake. I'd say the interesting ways in that we expose that data today, it is all we give you the straight snappy compressed Parquet files that we actually pull into Spark and process and move around on our own. But we do also give you the ability to stream out those records through an HTTPS interface and CSV or JSON or other formats as well, if you want to dynamically convert those to feed an application. So we've taken both the sort of the low-level access of just raw Parquet files at the S3 interface, as well as a sort of a more application-level API to get the JSON or CSV or other formats as well.
And what have been some of the most interesting or challenging aspects of building and launching Ascend that you have dealt with?
I think there's been a lot of really interesting and challenging aspects. One is obviously there's a pretty broad range of use cases that people have for data pipelines, and you get everything from people who are like, I have one file that is a truly, truly massive file and data set that has to crunch through on a particular cadence. Then you see other folks who literally are generating hundreds of millions of files across their data set that they're trying to push through Spark. And so the fun part as engineers is to actually take the sort of plethora of different use cases and access models and boil that down into a couple of these reusable patterns that we believe can actually fit multiple use cases at the same time and sort of refactor the problem scope, if you will, into just a handful of really powerful capabilities that give sort of a new layer and new platform to build on top of.
And what are some of the most interesting or unexpected lessons that you've had to learn in the process or edge cases that you've encountered while building Ascend, both from the technical and business perspective?
Yeah, I'd say, from the edge cases and so on, from the technical perspective, we placed a lot of bets really early on in the Kubernetes domain, and that's paid off tremendously well. One of the things that we've had to work hard on is the sort of various levels of Kubernetes support across the cloud providers. So, we will greatly relish the day when we can actually just run on all of the hosted Kubernetes capabilities that are like super tuned and optimized and on spot or preemptible instances. As we'd love to get away from having to manage a lot of that. We're not quite there yet, and so having to build up a lot more expertise around managing on the infrastructure side is for example, one of those areas. I would say on the non-technical side, or I guess I would say pseudo-technical side, there's been a really interesting investment on our side of how do we have a really high output, really high skill set team on the product and engineering side, where we create a different model that we've seen with a lot of other startups, where we've gone not the classic agile and scrum methodology, where it tends to be team and code base centric, but we've shifted really successfully to a model that is much more agile based off of projects itself. And so we find that teams end up coming together and dispersing very quickly based off of the projects they're working on. really towards some goal and some outcome of a new feature that they're building or a new capability. And one of the things that we found coming off of this is the output and what we're able to accomplish is really, really remarkable by comparison. The teams find that we're in fewer meetings, we're moving faster, we're launching more features, and probably the coolest part is um, everybody gets to own big capabilities that they get to drive all the way through. And so we're finding really across the board that especially for a fast-moving startup such as ours, that model of product management and software engineering has really been far more fruitful and exciting for us.
And then, in terms of the overall capabilities of the system or business success that you've achieved so far, what are some of the elements that you're most proud of? And in terms of feature sets or capabilities, any that have gained the greatest level of adoption?
Yeah, I'd say not too surprisingly, the last two capabilities we've announced have been really, really popular. Both are queryable data flows. Uh, we were actually shocked a little bit when we launched it. We quietly launched it to see if folks would notice. Um, Not too many folks really discovered it inside of the product, but once we actually started to socialize it with our users, we've been shocked as to how much they're using this queryable data flow approach. It just makes it so much faster to build pipelines. So we've been really happy to get the metrics off of that. And then the structured data lake has been really awesome. Like it honestly, it makes it so much easier to connect into so many other parts of the ecosystem. And we're super stoked about that. And then I'd say, honestly, the last part that's been really fun to watch has been we just started to open up a lot more of tutorials and how to's on the product, a bunch natively integrated into the product, a bunch more on our dev portal. And we're seeing people really gravitate towards using those as a way of testing out the platform and self-serving on it. That's been really cool to watch.
And in terms of the current state of the system, what are some of the sharp edges that remain, and when is Ascend the wrong choice for a given project?
Yeah, that's a great and super fair question. I'd say the easiest one that we see a lot of the time is if your data volume is either moving or evolving slow enough, or frankly could fit inside of a data warehouse, I'd honestly recommend keep your data there. Building pipelines is harder and more challenging. We're working super hard to make it way easier to build pipelines. But we see a lot of folks who honestly their data can and should fit inside of a warehouse and you should do it. And then I'd say there becomes a point in time where it really makes sense to build pipelines. You're doing more advanced or sophisticated things on your data, or the volumes are getting larger. And we oftentimes find folks who have massive data sets that definitely don't belong inside of a data warehouse, and the things are either crumbling or they're just spending insane amounts of money on that. And that's probably usually 6 to 12 months later than they should have started moving to pipelines. But that becomes a really good time to then change gears and really look at whether it's an Ascend or another technology, but getting it out of the warehouse.
And then looking forward, what do you have planned for the near to medium term future of Ascend, and any trends that you see in terms of the industry that give you inspiration for the long term future of the platform?
Yeah, there's a couple of trends that we see that I think are going to be really impactful. One is obviously the move to multi-cloud. We see a lot of interest across the ecosystem of being able to run not just in one cloud, but across all of them in ways that treat each cloud, region, or zone really as a micro data center with localized compute and storage with intelligent movement of data based off of dependencies. And so we see that as a really interesting domain. The other area that we see that is really interesting is, we use Spark heavily, but there's a ton of other technologies out there that open up a whole world of other use cases that are really interesting for us. Everything from TensorFlow to Kafka to Druid, all of these open up different use cases and different capabilities, for example, and many other technologies that are out there. And this is part of why we architected and designed Ascend this way was really as a control plane. While we can orchestrate, we also have the ability to orchestrate across different storage layers and across different processing layers and analyze and monitor access patterns of how users are tapping into data, and as a result can do really optimal things that you ordinarily couldn't do if you were just pulling data off of disk. And so doing things like intelligently building profiles off of how you're querying your data and perhaps moving it into Druid or moving it into a more memory-backed storage layer are things that we can really start to do and extend out that the underlying compute infrastructure to the appropriate tools and technologies dynamically. So those are both areas that we're really excited about.
And are there any other aspects of the work that you're doing at Ascend or other aspects of the idea of declarative data pipelines or anything along those lines that we didn't discuss yet that you'd like to cover before we close out the show?
I'd say the thing that we're really observing is, as we start to look into 2020 and see a lot of the sort of big efforts and initiatives that we're all putting into data engineering, the shift from more imperative-based systems to declarative-based systems, we've seen across a bunch of other technology landscapes. And what we're finding is for most teams and most companies, as we get more and more use cases, more and more data, and more people all contributing to those data pipelines and that data network inside of our various companies, we just get an exponential increase in complexity. And what has helped actually alleviate the pains and the late night or early morning pages that we get that wake us up when we really don't want to be working is that complexity and trying to battle with it. And what we've seen is that shift to these declarative-based models allows us to just write cleaner, simpler, more compact code and more elegant systems as a result. And I think we're going to see that really become increasingly important as, frankly, just data engineering gets more and more popular.
Well, for anybody who wants to follow along with the work that you're doing and get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I'd say that the biggest gap at the end of the day is being able to answer the question. Well, I guess I'll put it a couple of questions is, what data do I have? How was it generated? And where did it come from? Because if we can't answer those questions, it's really hard to build systems that are more automated. It all then falls back on us as engineers. So we have to be able to build technology that can answer those questions.
Well, thank you very much for taking the time today to join me and discuss the work that you've been doing with Ascend. It definitely looks like a very interesting platform that's solving a lot of painful pieces of data management in the current landscape. So thank you for all of your efforts on that front, and I hope you enjoy the rest of your day.
Thanks so much. You too, Tobias.
Thank you for listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.